In today's data-rich environment, machine learning engineers and data scientists frequently encounter datasets with numerous features. While these high-dimensional datasets contain valuable information, they also present significant computational and analytical challenges. This presentation explores how dimensionality reduction techniques help solve these problems by transforming complex datasets into simpler representations while preserving essential patterns. We'll examine core methods like PCA and SVD, and demonstrate their practical applications with real-world examples from image processing to recommendation systems. What is dimensionality reduction? Simplifies models. Reduces model complexity, helping prevent overfitting and improving generalization. Reduces computation time. Decreases training time and resource requirements for machine learning algorithms. Removes noise. Filters out irrelevant variations in data, focusing on meaningful patterns. Improves visualization. Enables effective visualization of high-dimensional data in 2D or 3D space. Dimensionality reduction transforms your dataset by projecting it into a lower dimensional space while retaining its key characteristics. This process is essential for pre-processing and unsupervised learning tasks like clustering and anomaly detection, where patterns must be identified without labeled examples. The curse of dimensionality. Computational complexity. Exponential increase in computational resources needed. Visualization challenges. Impossible to directly visualize beyond 3 dimensions. Increased sparsity. Data points become sparse and distances less meaningful. As dimensions increase, the volume of the space increases so quickly that available data becomes sparse. This phenomenon, known as the curse of dimensionality, makes finding patterns increasingly difficult. For example, in a 10,000 dimensional space, even millions of data points become effectively isolated. Dimensionality reduction addresses this challenge by transforming features into a lower dimensional space that preserves the essential structure of your data. This transformation makes pattern recognition more computationally feasible and statistically reliable. Principal component analysis. Standardize data. Normalize features to have zero mean and unit variance. Compute covariance matrix. Calculate how features vary with respect to each other. Calculate eigenvalues and eigenvectors. Find directions of maximum variance in the data. Project data. Transform original data onto new principal component axes. PCA transforms your data into a new coordinate system where the first principal component captures the highest variance in the data. Each subsequent component is orthogonal to the previous ones and captures decreasing amounts of variance. This technique is particularly valuable when you need to reduce dimensions while preserving as much variability as possible. For example, in customer segmentation, PCA can reduce hundreds of customer attributes to a few key dimensions that capture essential buying patterns. PCA in facial recognition. Eigenfaces. PCA identifies base components, eigenfaces, that represent facial features across a dataset. These eigenfaces capture the most significant variations in facial structure. Dimension reduction. A 100 by 100 pixel face image with 10,000 dimensions can be represented using just 50 to 100 eigenface components, dramatically reducing computational requirements. Recognition process. New faces are projected onto the eigenface space and compared against known faces using their reduced dimensional representations, enabling efficient identification. Facial recognition exemplifies PCA's power in real-world applications. By decomposing face images into eigenfaces, we transform a high-dimensional pixel space into a compact representation that captures essential facial characteristics while discarding noise and redundant information. Singular Value Decomposition. Matrix decomposition. Decompose matrix A into U, sigma, and V transpose. Dimensionality reduction. Keep only largest singular values. Data reconstruction. Approximate original matrix with reduced components. SVD decomposes a matrix A into 3 matrices, U, which contains the left singular vectors, sigma, which holds the singular values, and V transpose, which contains the right singular vectors. By keeping only the largest singular values and their corresponding vectors, we achieve dimensionality reduction while minimizing information loss. This technique is compelling for recommendation systems, where user-item interaction matrices are typically large and sparse. Netflix's recommendation algorithm famously utilizes SVD to decompose user movie rating matrices into latent factors that represent user preferences and movie characteristics. PCA versus SVD, when to use each. Characteristic. Data centering. Requires centered data. Works with raw data. Matrix requirements. Works with square matrices. Works with any matrix. Computational efficiency. More efficient for smaller datasets. More efficient for sparse matrices. Primary applications. Feature extraction, visualization. Recommender systems, text mining. While PCA and SVD are mathematically related, PCA can be implemented using SVD. They serve different use cases in practice. PCA focuses specifically on finding directions of maximum variance in centered data, making it ideal for exploratory data analysis and visualization tasks. SVD offers greater flexibility as it works with any matrix without requiring centering. It excels in applications like collaborative filtering for recommendation systems and latent semantic analysis for text mining, where uncovering latent factors in the data is the primary goal. Dimensionality reduction, practical applications. Image processing. Efficient compression and facial recognition. Text mining. Topic modeling and document classification. Recommender systems. User preference modeling in e-commerce. Bioinformatics. Gene expression analysis and protein structure prediction. Dimensionality reduction techniques have become essential tools across numerous domains. In genomics, researchers use these methods to analyze high-dimensional gene expression data with thousands of genes but relatively few samples. Financial analysts employ them to identify patterns in market data with hundreds of indicators. As data continues to grow in volume and complexity, mastering dimensionality reduction becomes increasingly valuable. By thoughtfully applying these techniques, data scientists can extract meaningful insights from seemingly overwhelming datasets, enabling more effective pattern recognition and predictive modeling. Summary: Dimensionality reduction and PCA. High-dimensional data challenges. Modern datasets with many features cause higher complexity and analysis issues due to the curse of dimensionality. Purpose of dimensionality reduction. These techniques reduce variables while preserving key information, making data easier to visualize and analyze. Core techniques, PCA and SVD. Principal component analysis identifies directions, also known as principal components, that capture the most variance in the data. Singular Value Decomposition is a matrix factorization method that breaks down data into simpler, interpretable components. Preserving essential patterns. These methods reduce dimensions but keep key patterns vital for analysis and model performance. Real-world applications. Dimensionality reduction is widely applied in fields such as image processing, for example, face recognition, noise reduction. Recommendation systems, for example, compressing user-item interaction matrices for collaborative filtering. Enhancing unsupervised learning. Simplifying data boosts the performance and clarity of unsupervised algorithms like clustering and anomaly detection. Strategic tools for data scientists. Dimensionality reduction is key to handling complex data and gaining valuable insights. Thank you and upcoming module, Deep Learning. We truly value your active participation in our machine learning journey. Next session, we'll dive into Module 5, Deep Learning. This module will provide a comprehensive exploration of neural networks, starting with the fundamental principles and structure of basic neural networks, and progressing to more sophisticated and advanced architectures. We will examine how these models function, their key components, and their practical applications in solving complex machine learning problems. Stay connected. Subscribe, like, and share to continue your learning adventure.